Hello, and welcome to this lesson on further concentration calculations. In today's lesson, we will first walk through the steps of how to calculate the concentration of a solution. Before we use the relationship between moles, volume, and concentration to solve some problems involving reacting solutions ourselves. So far, you've learned how to calculate the mass or moles of a solute in a solution. You are now familiar with the basic principles of determining the amount of substance present in a solution, which has provided you with a solid foundation in quantitative chemistry. Building on this foundation, today's lesson will enhance our chemical understanding by introducing the concept of calculating the concentration of a solution when two solutions react completely. Let's dive into a crucial technique in quantitative chemistry: calculating the concentration of a solution when the volumes of two solutions that react completely are known, and the concentration of one of these solutions is known. This might sound complex, but it's quite manageable if you break it down into a series of logical steps. First, let's understand the fundamental idea here. When two solutions react completely, the stoichiometry of the reaction determines the relationship between the volumes and concentrations of the reactants. Stoichiometry is the relationship between the weights of reactants and products before, during, and after chemical reactions. The stoichiometry comes from the balanced chemical equation of the reaction, telling us the ratio in which the reactants combine. Let's understand this with an example. Suppose we have 25 centimeters cubed of hydrochloric acid, HCl solution with a concentration of 0.1 moles per dm cubed, and it completely reacts with 50 centimeters cubed of sodium hydroxide, NaOH solution. We need to find the concentration of the NaOH solution. This follows the equation: hydrochloric acid, HCl, plus sodium hydroxide, NaOH, turns into sodium chloride, NaCl, plus water, H2O. To calculate the unknown concentration, we must first start with identifying what we know. Volume of HCl, V1 in the table here, is equal to 25 centimeters cubed, which is 25 1,000ths dm cubed. This is a 0.025 dm cubed. The concentration of hydrochloric acid, C1 in the table, is 0.1 moles per dm cubed. And the volume of sodium hydroxide, V2 in the table, is 50 centimeters cubed, which is the same as saying 51,000ths dm cubed, or 0.05 dm cubed. So the question tells us the volumes of both solutions and the concentration of one. To find the concentration of the unknown, NaOH, we will first calculate the moles of the known solution, HCl. This table at the bottom sets out what we know and what we need to find out. Remember, the equation triangle shows that the number of moles is given by the formula number of moles equals the concentration multiplied by volume. Now, let's use this formula to calculate the number of moles of HCl. We need to do the concentration of HCl multiplied by its volume. To work this out, we do 0.1 moles per d m cubed multiplied by 0.025 dm cubed. So the number of moles of HCl is 0.1 multiplied by 0.025. Therefore, we get 0.0025 moles. Let's fill that into our table. Great work! We have now worked out all of the values for HCl. We can now use stoichiometry to find the moles of the unknown solution. In our case, the unknown solution is NaOH. Because the chemical equation is balanced, the mole ratio of HCl to NaOH is 1:1. Since the mole ratio is 1:1, the moles of NaOH is the same as the moles of HCl, which is 0.0025 moles. So NaOH is also 0.0025 moles. Now that we have worked out the moles of both solutions, we are ready to find the concentration of NaOH. To calculate the concentration of sodium hydroxide, we first need to look back to the equation triangle and use the equation. concentration is equal to the number of moles divided by the volume. So the concentration of sodium hydroxide is equal to the number of moles of sodium hydroxide divided by its volume. This means that the concentration of sodium hydroxide is equal to 0.0025 moles divided by 0.05 dm cubed. When we calculate this, we get an answer of 0.05 moles per cubic decimeter. Thus, the concentration of the NaOH solution is 0.05 moles per decimeter cubed. By following these logical steps, you can calculate the concentration of an unknown solution when given specific volumes and the concentration of another reactant. This method relies on the concept of moles and the stoichiometry of the chemical reaction, offering a systematic approach to solve such problems in quantitative chemistry. Remember, practice makes perfect. Let's look at some questions to put what we have learned today into practice. 40 centimeters cubed of sulfuric acid of concentration 0.2 moles per decimeter cubed reacts completely with 80 centimeters cubed of potassium hydroxide, KOH. Calculate the concentration of the potassium hydroxide solution. First, let's identify the given information and write it out in a table. The volume of sulfuric acid is 40 centimeters cubed. To convert this to dm cubed, we divide 40 cm cubed by 1000, which becomes 0.04 cubic decimeters. The question also tells us that the concentration of sulfuric acid is 0.2 moles per decimeter cubed, and also states that the volume of KOH is 80 cm cubed. Converting to dm cubed, we divide by 1000 to get 0.08 dm cubed. And now we need to find the concentration of KOH. Pause the lesson here and have a go at this question. To find the moles of sulfuric acid, we multiply 0.2 moles per decimeter cubed by 0.04 dm cubed to make 0.008 moles. According to the balanced equation, 1 mole of sulfuric acid reacts with 2 moles of KOH. Therefore, the moles of KOH will be the amount of sulfuric acid, which is 0.008 moles, multiplied by 2, which makes 0.016 moles. Great! We can now calculate the concentration of KOH. Remember, we are using the equation concentration is equal to moles divided by volume. The concentration of KOH is 0.016 moles divided by 0.08 dm cubed, which is 0.2 moles per decimeter cubed. So, the concentration of the potassium hydroxide solution is 0.2 moles per decimeter cubed. Let's look at one more question. Suppose we have a complete reaction between 30 cm cubed of nitric acid, HNO3, of concentration 0.15 moles per decimeter cubed, and 45 cm cubed of calcium hydroxide, CaOH2. Calculate the concentration of the calcium hydroxide solution. This equation is 2HNO3 reacting with CaOH2, becoming CaNO32, and 2H2O. First of all, identify the information given in the question. Let's write this in a table like we did for the last practice question. The volume of HNO3 is 30 cm cubed. We can convert this into dm cubed by dividing 30 by 1000 to get 0.03 dm cubed. We also know from the question that the concentration of HNO3 is 0.15 moles per cubic decimeter, so let's add this to the table. The question also states that the volume of CaOH2 is 45 cm cubed. We Sienna convert this to dm cubed by dividing 45 by 1000, which gives 0.045 dm cubed. Again, add this to the table. And we need to find the concentration of CaOH2. Pause the lesson here and try this one out. To calculate the moles of HNO3, we will calculate 0.15 moles per decimeter, cubed multiplied by 0.03 dm cubed to make 0.0045 moles. According to the balanced equation, 2 moles of HNO3 react with 1 mole of CaOH2. Therefore, the moles of CaOH2 will be half those of HNO3. So to find the moles of CaOH2, we divide 0.0045 by 2 to get 0.00225 moles. Finally, we can work out the concentration of CaOH2. The concentration of CaOH2 is the moles divided by the volume, which is 0.00225, divided by 0.045 to get 0.05 moles per decimeter cubed. Great work on those questions. But why is this important? Well, advanced concentration calculations are crucial in many fields, from developing new medicines to monitoring pollutants in environmental testing. Chemists use these precise calculations to make sure everything is safe and effective. It's a perfect example of how chemistry is essential in making a real difference in the world. In today's lesson, we delved into the process of calculating the concentration of a solution when you know the volumes of two solutions that react completely and the concentration of one of the solutions. We outlined the steps required to find the unknown concentration. First, by identifying what information we had. Then we calculated the number of moles of the known solution using its concentration and volume. Using the stoichiometric coefficients from the balanced equation, we determined the moles of the unknown solution that would react with the given moles of the known solution. Finally, we calculated the concentration of the unknown solution by dividing the number of moles by its volume. By mastering these steps, we can now confidently determine the concentration of an unknown solution in a chemical reaction, an essential skill for accurately preparing solutions and understanding chemical reactions in various practical and laboratory settings.